Circular motion and gravitation. All right, so unit 3, by far our best unit so far. Okay, unit 4 could be even better. We'll see how tomorrow goes. Okay, but so far our best unit performance-wise. Main topics for this unit. First thing we covered was uniform circular motion. Okay, so there's some stuff in the multiple choice about the principles behind this. All right, so that would be things like for an object to travel in a circle, it has to be experiencing a constant force directed towards the center. Its velocity is always changing, but its speed is constant. Okay, it's always accelerating towards the center. Okay, things like that. Those are the principles of uniform circular motion. Okay, that those things have to be present in order for it to be uniform circular motion. So stuff like that. Okay, then we talked about some formula stuff. Okay, and we said that 2 pi r over t equals the speed at which something traverses a circle. So the circumference of the circle divided by the period gives us the speed of the object moving around the circle. Okay, we also talked about t equals 1 over f and f equals 1 over t. We talked about that first day as well. Okay, so period is the time for one cycle, but frequency is the number of cycles per time interval. Okay, usually seconds. So those are things that we have to remember. We also talked about centripetal acceleration, which was a concept we barely ever talked about. Okay, I think in all the time we spent in that unit, you might have done like 3 problems that had to do with AC equals V squared over R, which means it's pretty unimportant. Okay, in terms of like problem solving and stuff for your final exam, but it is something that we covered. Okay, mostly we covered it though so that we could go to this. Okay, and that is that F net equals mv squared over r. In other words, mass times centripetal acceleration. Okay, and that F net was our centripetal force. Okay, so that was the stuff we covered kind of in terms of how circular motion works. So there'll definitely be some multiple choice stuff about the nature of uniform circular motion. As we talked about uniform circular motion, we went into 2 examples, right? We talked about unbanked curves. Okay, what holds you in an unbanked curve? Friction. All right, so in other words, the centripetal force keeping you in that circle is provided by the force of friction. Okay, and we did a lot of problems on unbanked curves, so there's a pretty high likelihood that there could be one on the final exam. Okay. That same day, we talked about banked curves as well. Okay, and we use banked curves so we don't have to rely on friction, for days like today, where the ground is covered in this like sheet of really slippery ice that's making life difficult. All right, so bank curves help us to eliminate the need for friction by simply banking the corner, okay, and using the normal force instead, right? And our formula for that was tan of theta equals v squared over r times g. Okay, so there could be something in the multiple choice about bank curves, okay, possibly written response, but more likely multiple choice. Okay, just make sure you understand how bank curves work. Okay, then we talked about artificial gravity. Okay, artificial gravity uses a spinning drum or cylinder of some kind, okay, in order to use your inertia and the normal force of the inside of the drum to produce a feeling like gravity. It's not really gravity, but it produces a feeling like it because if I'm standing on the inside of a spinning drum, and I'm like E.T. because I have this really long neck apparently, so I can't draw very well. That really looks like E.T. But okay, he's gonna phone home. Okay, anyway, we want to go like this, okay? Our inertia wants us to go in a straight line, okay? But The inside of the drum prevents it and pushes straight back towards the center, giving us a feeling of weight against our feet. Okay, it's not real gravity, but it's a feeling like it. In that case, we want the centripetal force to feel like the force of gravity, and it usually ended up with, mv squared over r equaled mg, and then we were solving for either how fast the station had to spin or what the radius of the station would be or something like that. Okay, so could be one like that on the final exam as well. Okay, we did spend a day talking about how artificial gravity works. Questions so far? Okay, don't be afraid to interrupt me and ask as we go. All right. Fourth thing we talked about was non-uniform circular motion, or vertical circular motion. And we spent a bit more time on that than we did on the uniform stuff. All right, what's the main rule for vertical circular motion? What does Fc equal in vertical circular motion? Forces in minus forces out, right? In other words, we're calculating the net force, okay, for circular situations. We dealt with 3 different places within the circle, all right? So we dealt with top on the inside, okay? You have to have a certain minimum speed in order to do this part of the circle. All right. When you are going just fast enough at that minimum speed to stay in the circle, only gravity is acting as a centripetal force. Okay. If you're going faster than the minimum speed, then you're adding in what other force? Normal force, right? Because if you're going faster than the minimum speed, you do push on the track pushes back towards the center. There are no forces out in this situation. Okay, there's either just going to be gravity or there's going to be gravity plus normal force, okay, if you're going faster than the minimum speed. One of the other places we talked about was the bottom of the circle on the inside. Okay, this is where you feel heaviest because this is also where you're going the fastest usually. Okay, so we would have gravity acting out of the circle, normal force or tension depending on the situation acting back in towards the center. Okay, so Fc equals forces in minus forces out, normal force minus gravity for that situation. Okay, and the third situation we talked about is the one that can produce a feeling of apparent weightlessness. Okay, we watched the video, lots of videos on going over the top of a vertical circle. Okay, gravity acts in, normal force acts out, unless I go fast enough that I lose contact with the track and then I feel weightless. I'm not actually weightless, but I feel that way. Okay, so we can produce a feeling of apparent weightlessness going over the top of a vertical circle. Okay, that ringing a bell for everybody? I would expect one of these for sure in the written response. Okay, there may also be a multiple choice question about it, but for sure you're going to have a vertical circular motion question in the written response part of the exam. That was 4, right? Okay, the next thing we talked about, universal gravitation. Okay, so that is that the force of gravity is influenced by the universal gravitational constant, the mass of the 2 objects that are interacting, and their separation distance squared. Okay, those are the things that can affect the force of gravity between 2 objects. That's something important to remember because that could certainly end up in the multiple choice, that the force of gravity is a mutual attractive force, not a force of the big thing on the small thing. Okay, it is a mutual attractive force between the objects. Okay, on your unit exam, this was tested with the sun, moon, earth question, and you had to find the net gravitational force acting on the earth given the orientation of sun and moon. I would say on the final exam, there may not be a written response question about just the universal law of gravitation, but it is part of satellite motion, so it is something you need to know. Okay, so there will certainly be some multiple choice stuff about the universal law of gravitation, okay, and it is part of satellite motion and things like that, so it's something we need to know, okay, because we have to be able to use it in that situation. All right, everybody with me on that? Okay, so the multiple choice questions might ask something like, you have two masses interacting and you double how far apart they are. What will happen to the force of gravity between them? Okay, what will happen to it? If I double how far apart they are, the force of gravity between them will be 4 times less, right? It's exponential, right? If I double r, I'm dividing by a number that's 4 times bigger, so I'll have 4 times less, or 1/4 of the gravitational force between them. Okay, after universal gravitation, then we talked about satellite motion. Okay, where the force centripetal is provided by the force of gravity. Okay, that could be mv squared over r equals big G times m1 times m2 over r squared. Or if we aren't given v and no way to calculate it, then we sometimes have to substitute in, okay, this 2 pi r over t for v, and that looks like this: m 4 pi squared times r over t squared equals big G times mass 1 times mass 2 over r squared. Okay, so expect there'll be some multiple choice stuff about satellites, but definitely there'll be a satellite question in the written response. And I would say in all likelihood, I would bet on having to do the substitution. Which mass cancels in a satellite question? The mass of the satellite, because all things fall at the same rate. Okay, so the mass of the satellite is irrelevant and will always cancel in a satellite motion problem. Okay, the mass that stays is the mass being orbited, Earth or the sun or whatever. Okay. All right, after satellite motion, we quickly talked about Kepler and Cavendish. Okay, I would say they're game for multiple choice, but nothing else. Okay. Certainly, Kepler's law of periods is, it's all nice and everything if you've got the right information, but you don't always have the right information. So if you're doing a satellite question, I would go with satellite motion to solve it as opposed to Kepler, okay? Because I would probably make it so that you couldn't do it with Kepler if it was me making up the test. And oh, wait, it was me making up the test, so I would probably go with that one. Does Nancy know that? Okay. Make sure you sign out with her, because I haven't got any email to that effect. Okay, that making sense there? All right, after Kepler and Cavendish, okay, remember Cavendish is the guy who discovered big G, or was actually able to calculate it. Okay, he had the torsion balance, okay, with the pith balls and the lead balls, and they were attracting each other and creating that torque. Okay, and then after that, we talked about gravitational field strength. Right, gravitational field strength is acceleration due to gravity, okay, at any point. So it's little g equals big G times the mass times r squared, okay, and remember that that's the mass of the object generating the gravitational field, the larger of the two. Okay. Okay, we did have a problem-solving question on that on the unit exam. I don't know if it's necessarily going to be something that makes it onto the final exam written response, but it would certainly be something that would be on the final exam, probably in the multiple choice. Okay, that's it. That's what was in there. Okay, there were 8 major topics in circular motion. Okay, 3 more than there were in dynamics, even though that unit took less time. Okay, there just wasn't as much detail in each one. All right, so questions from you guys. Anything you want me to go over in more detail, show a demonstration of?
Let's do a gravitational field strength.
A gravitational field strength question? Okay. Okay, so how far from the Earth's surface is an object if it experiences an acceleration due to gravity of 6.72 meters per second squared? All right, so we have little g, 6.72 meters per second squared. We're looking for how far from the surface. Of course, the formula won't give me that. The formula will give me how far from the center. So I'll have to do one more operation after that. Okay, and I know I'm dealing with the Earth. All right, so little g equals big G times the mass of the Earth over r squared, and I'm looking for r. So that's going to mean big G times the mass of the Earth over little g square rooted. Okay, so we got 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, mass of the Earth, okay, divided by 6.72. Right, and then we're going to square root that. So. All right, so it's telling me that we're looking at 7,704,223 meters from the Earth's center. All right, so now if I want to get the distance from the Earth's surface, I need to subtract the Earth's radius from that. Okay, so we're looking at 1.33 times 10 to the 6 meters from the Earth's surface. Okay. All right, so that would be a typical one. And guys, that's I put that trick in there on purpose to remind you that sometimes with satellite questions, with gravitational field strength questions, you get that trick played on you about the surface, right? Or it's this altitude or this height. Okay, remember that means add or subtract the Earth's radius depending on the situation. Okay, what else? Right. Vertical circular motion question. Okay. Okay. There's a vertical circular motion problem. I want to know how fast an 1,800 kilogram car has to travel over a vertical circle with a radius of 150 meters for its apparent weight to be 1,500 newtons, okay, which is lighter than its actual weight. Right? So we are dealing with what part of the circle? Over the top, right? Okay, that's the only place where we can feel that way. Okay, plus it says over the top in the question. Okay, so we've got this situation here. We do have a normal force acting out, and it's 1,500 newtons. We have a force of gravity acting in, okay, that we haven't calculated yet, but it's not hard. Okay, 1,800 times 9.81, so 17,658 newtons. Okay, there's kind of my free body diagram. For all vertical circular motion, Fc equals forces in minus forces out. Okay, force in is gravity, the force out is normal force, and I'm looking for speed. So I've got mv squared over r equals m times g, which we've already done, so that's our 17,658 newtons, minus 1,500 newtons. Okay, so I want to get V by itself. So I'm going to multiply both sides by R, and then I'm going to divide both sides by M, and then I'm going to square root. Okay, so what I'll end up with is this, that V will equal the square root of 17,658 minus 1,500 times 150 meters divided by 1,800. Okay, and that will give me how fast the car has to go. Hopefully it's not a ridiculous number. Okay, so it's got to be moving at 37 meters per second in order for that to occur. Okay. Okay, what else? Richard? Bank curve question? Okay, so we're looking for the radius of a 12-degree bank curve that cars negotiate at 17 meters per second. All right, so we're given V, and we're given theta, okay, and we're looking for R. Okay, so our bank curve formula is that the tan of theta equals V squared over R times G, and we need to solve for R. So I'm just going to switch tan of theta and R. Okay, so R will be V squared divided by the tan of theta times G. So that'll be 17 squared divided by the tan of 12 times 9.81. Okay, so it's got to have a radius of 1.4 times 10 to the 2 meters. Okay. Is that all right, Richard? Is that all right? Okay. All right, what else? Cameron? Unbanked curve? Okay. Okay, so we're looking for the coefficient of friction of an unbanked curve with a radius of 89 meters. Okay, so we know radius. Okay, we know the speed it can be taken at is 12 meters per second, and we're looking for the coefficient of friction in this case. So we have to remember that obviously friction keeps you in an unbanked curve. Okay, so we know that Fc is equal to the force of friction. Okay, when we expand that out, it's mv squared over r equals mu times the normal force. Because this is not banked, normal force is equal to gravity. All right, so I'm looking for mu. So all I have to do is manipulate and bring mg over to the other side. The m's are going to cancel, okay, and I'm going to be left with mu equals v squared over r times g, just like I am with a bank curve formula. All right, so whatever is, holding you in the curve is always going to be calculated by v squared over rg, whether it's coefficient of friction or whether it's the angle of bank, either one. Okay, so we have here then 12 squared divided by 89 times 9.81. All right, so our coefficient of friction is 0.16 for that. And remember, there's no units on the coefficient of friction. Am I good, Cam? Okay. All right, what else, guys? Artificial gravity? Okay. I don't think I've ever asked one quite this way before, but we'll give it a whirl here. Okay, so I have a space station whose radius is 200 meters, spinning at 130 meters per second. And I'm trying to find out essentially how people will feel on board that space station as it spins. Okay, so for an artificial gravity question, we have Fc equals the force of gravity. Okay, that's what we want it to feel like. That means mv squared over r equals m times g. It's just this time g isn't going to be 9.81, or maybe it will be if I like miraculously pick the right numbers for that. Okay, probably not though. All right, so I'm solving in this one for g. Let's see what the acceleration due to gravity produced by this station will be. What's going to happen to the masses? They're going to cancel. So that's the extent of my manipulation. All I have to do is go 130 squared divided by 200. And I'm sensing that this is not going to be very good. Okay. People are going to die because they're going to experience an acceleration of 84.5 G's. Not good. Okay. Some engineer really screwed up on that one. Lots of flat astronauts. Okay, does that sort of make sense? That's what happens when you pick numbers out of your head. Okay, what else? Okay, satellites. So that would be a tough one because I only give you one piece. Well, I give you two pieces of information. I tell you it's Earth, and I tell you that the satellite is 4.2 times 10 to the 7 meters above the surface of the Earth. So what do I need to do first off? Right, I've got to get the proper radius by taking that number and adding the radius of the Earth to it. Okay, so I've got 4.2 times 10 to the 7, okay, plus 6.37 times 10 to the 6. All right, so my actual radius will be 4.837 times 10 to the 7 meters. Okay, so now I've got my actual radius that I can use. I'm looking for the orbital period of the satellite. For all satellites, FC equals FG. Okay, I can't use mv squared over r here because I don't have any way to calculate v. So I have to use the substitution method where I will have m 4 pi squared times r over t squared equals big G times the mass of the Earth times the mass of the satellite over r squared. Okay, so I'm trying to solve for the orbital period. So I'm going to multiply both sides by t squared because I want it on the top where I can solve for it. I'm going to multiply both sides by r squared, so I'll have r cubed over here. Mass of the satellite's going to cancel, and then I'm going to divide both sides by big G times the mass of the Earth. And then I'll square root. Okay. So what that'll leave me with is this, that t equals the square root of 4 pi squared times 4.837 cubed, or sorry, times 10 to the 7 cubed, okay, divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, the mass of the Earth. Okay, so 4 pi squared times not alpha, math cubed. Okay, so we're looking at a period of 1.1 times 10 to the 5 seconds. Okay, that's about as involved as they would get. Richard? Because I can't use this. I don't have V, and I have no way to calculate it. So what I did is I substituted this, which is the formula for V, in for V, but I had to square it because V was squared, right? So 4 pi squared, r squared, t squared, right? But there was already an r on the bottom, so the r squared canceled there. Yeah? Yep. Okay, what else? I think we've actually done one of everything that was on the board now. Okay, any other questions or things you want me to talk more about? Quinn? Okay, so with Kepler's law, okay, the big thing with Kepler's laws, plural, okay, is we need to know what the three are. Okay, so you got the elliptical orbits. Okay, so planets don't move in perfect circles. Their orbits are slightly elliptical, which means they move faster at some points and slower at other points. Right now, we're in the fast part, okay, of our orbit. Then we have the law of equal areas, which is basically mathematical confirmation of the elliptical orbits. So as a planet moves around in equal time intervals, it sweeps out an equal area of its orbit. So in the places where it's going slower, that sector is smaller than in places where it's moving faster, right? So the radius will be smaller, but the outer edge of the arc will be bigger. Okay, and then there's the law of periods. Okay, and that was the T1 squared over R1 cubed equaled T2 squared over R2 cubed. Okay, any two bodies orbiting the same central point have that relationship between their radii and periods. Okay, and then you're manipulating if you're using that. Okay, I would say it's not likely you'll get a final exam problem where Kepler's law would apply. All right, what else? I think I said it was 21 multiple choice and 12 written. Let me just double check. "21 multiple choice and 12, yeah, and 12 written. Yeah. So in the written response, there are 65 marks from those 12 problems. So they're on average about 5 marks each, right? No. Well, we've never done a numeric response. In Physics 20, I wouldn't throw something new at you on the final. What's that? Yeah. But it's true. But next year, you will definitely have some. Mr. Dickey uses a lot of numeric response. All right. Anything else there, guys? All right. Reminder, what do you need to bring to the test? Calculator with good batteries, several pencils, and then if you need to have a snack or something like that. Okay, don't bring your formula sheet. You're getting a fresh one. Okay, I don't know how much stuff you've written on yours or if it even still exists. So make sure you don't bring anything other than what you're going to write with, especially your phone, your smartwatch, whatever. Okay, that can't come with you into the test. Please leave it elsewhere. All right, well, you got some time to look at the review there. Okay, hopefully some more questions will come up while you're working on that. Okay, and I'm happy to answer any more questions that you might have on that. Okay, remember our review session, guys, is going to be January 23rd, okay, from 11 to 1 p.m. Okay, I'm not going to be doing what I'm doing today, okay, or I've done the last couple of days where I'm reviewing all the units because I'll have already done that. This is going to be, you've got questions, I'm got answers. Okay, so come in and you're specifically asking for help, or you're wanting to look over your old unit exams because they'll have them out during that time. Okay, whatever that is, but it's not going to be a like organized review of me talking up front. It's going to be, you came in for help, I'll give you help specifically. Okay. All right, so here's what we know. Whoop.